Okay, good morning students. As you know, my name is Sud Pandey and you are floating with me in the world of physics. Okay, as you know, we are going through physics and as you know that today I will start a new chapter for you, and the chapter name is fluid mechanics. Okay, so basically in fluid mechanics we will discuss about the mechanics of the fluids. So as you know that in the mechanics we will discuss basically about the mechanical energy. What the sense of the mechanical energy? The sense of the mechanical energy is that we considered here the mechanical energy. Okay, it means in short we can say that if we consider the situation means either the fluid is at rest or it is in motion, so this comes under the mechanics. So in fluid mechanics we will discuss about the all aspects in the reference of the position of the particular fluid. Okay, so I hope that the word fluid mechanics is clear to all of you. Okay, once again, fluid mechanics is a branch of physics in which we discuss about the position of the fluid. It means the fluid is at rest and what type of property it will associate, and if the fluid is in motion, then what type of properties will it associate. Okay, so firstly we will discuss about the fluids. What are the fluids? So for that we have certain important points as you can see on your screen, and the first point is written clearly that matter is broadly divided into three categories: solid, liquid and gaseous. It means in the complete world we have matter, and the matter can be divided into three major parts. So the major parts are solid, liquid and gas. Okay, what to make them differ? This is the basic question, and the answer you know very well. The answer firstly you gone through, and I suppose that you all will be in class 9th or little bit in class 8th. Okay, so the answer comes from class 8th or 9th, and here it is. So the interatomic force, this is the thing which makes them differ from one another. Okay, so interatomic force is strong in solid as it is written here, you know very well. What does it mean? It means let's suppose we have a lattice of the solid like this way. Okay, and these are the atoms of the solid like this way. Okay, so if we see, then we find that there is no separation between the atoms of the solid. It means interatomic separation is negligible. Okay, and the force between the atoms is too strong. But if we consider a case of liquid and also a case of gas here, then the separation in liquid like this way. Okay, whereas in gases like this way. It means the interatomic separation is very large in the case of gases, but if we compare the interatomic separation between the solid and between the liquid, then we find that the interatomic separation is quite larger with compared to the solid in liquids. Okay, now what? Due to the interatomic separation, due to the interatomic forces, we can simply say that any object, any matter can acquire shape and size. It means because the solid has the maximum force and gas have the minimum force, and the liquid has, we can say, intermediate force. Okay, so uh, maximum interatomic force is in solid, medium interatomic force is in liquid, and the minimum interatomic force will be in the gases. It means all the solid must have a definite shape and size, whereas in case of liquid, we can simply say that the shape can be changed. In case of liquid, shape can be changed. Okay, but in case of solid, it can't be changed. Okay, so here we can change the shape, but volume remains constant. Volume remains constant. So this is the main thing. So volume remains constant in case of liquid. Shape and size can be changed. In case of solid, shape and size, volume, each and everything remains constant. Whereas if we talk about the gases, then in case of gases, shape, size, volume, everything can be changed. Okay, so these all things you know very well. Now what we will discuss, that in this chapter we shall assume, because as I have already told you that we have to focus on the situation, on the position or the state of the fluids. So we have certain criteria before we start the journey. Okay, and what are the criteria? The criteria is so simple that whatever a liquid we will deal with are incompressible and non-viscous. So this is the point you should remember, that in fluid mechanics we consider the fluid as incompressible and non-viscous. Now what is the mean of the incompressible? What is the mean of non-viscous? So basically the first condition that is incompressible. So the first condition means that the density of the liquid is independent of the variation in pressure and always remains constant. It means we consider here that the density or rho is always constant throughout the study of in fluid mechanics. Okay, so this is called the incompressible. So I hope that up to here each and everything is clear to you. Now the second is your non-viscous. So what do you mean by non-viscous? As I have already told you that viscosity, what is viscosity, what is viscous force. So I think and I suppose that you can easily handle about the non-viscosity. Okay, but yet I will tell you the second condition, that is non-viscous. What does it mean? It means that the part of the liquid in contact do not exert any tangential force on each other. It means let's suppose this is the layer of the fluid, this is the another layer of the fluid, like this way, and both layers are considered either at rest maybe, or we can say either in motion. And if there is no friction force between them, there is no viscous force between them. Okay, so viscous force is basically the friction force which opposes the relative motion between the layers of any fluid. Okay, so it means we can simply say that if we consider that there is no viscous force, that is the non-viscous or non-viscosity. Practically it is not possible. Okay, we know that practically it is not possible that any fluid have viscous force that equal to 0. Okay, because if without the viscous force, as without friction force we can't move on the surface of the earth. In the same way, the one layer cannot float on the other layer of the fluid without the viscosity. Okay, it means practically viscosity must be there, but in theory we assume that the viscous force is zero. It means this is the ideal condition what we have to take here. Okay, so we have an ideal fluid, we can simply say in a single word. So ideal fluid is basically a fluid which is incompressible. It means the density remains constant, and non-viscous, it means the friction force in between the layers, or we can say the viscous force in between the layers becomes zero. Okay, so these two basic characteristic is considered as a fluid to be ideal. Okay, so in this complete journey of the fluid mechanics, we take every fluid as an ideal fluid. So I hope that up to here each and everything is clear. Now, first property of the fluid, any fluid, means we have a point to explain you that here it is written that liquids and gases together are called fluids that which can flow. So fluids contains liquid as well as gases, means the matter which can flow is fluid. Okay, so fluid has several properties, and the first property is pressure. What is pressure? That is the basic thing, I suppose, and you have read it about pressure in class 9th or in the class 8th, maybe in class 7th. Okay, so the pressure or its definition is quite easy. For that we will consider a liquid container. Okay, so suppose this is your liquid container like this way, and we fill this container with a liquid. Okay, this is your container having liquid in it like this way. So I hope that now this is looking so good, so nice. Now what? Firstly, we have to consider a point A inside the fluid. Okay. Now question, why we take a point inside the fluid? Because we have an ideal fluid. It means we can simply say that any point can be considered as the part of the fluid. Okay, so it means if we consider a part of the fluid or just a point inside the fluid, the significance is quite similar. Okay, that's why we are taking here a simple point. Let be the point is A. As you can see here, this is your point A inside the fluid. This be your point A. Okay, now we consider a small area, that is delta S. So the delta S is the very small area which encloses the point A. So this is basically your area which having the point A at which we have to calculate the pressure. So according to the definition of the pressure, we can simply say that the common magnitude of force taking Bf, the pressure of fluid at point A is defined as pressure force per unit area. So pressure, and that is force upon area. So pressure per unit area, per unit cross section area, whatever you can say, okay, is considered as, okay. So pressure is nothing but whatever amount of force is there and applicable in per unit area. So force per unit area gives the pressure. Okay, or we can simply say that if we multiply the pressure with the area of surface area, then we get the force experienced by the layer due to the pressure existed on that layer. Okay, so in one word we can simply say that pressure is nothing but it is equal to force per unit area. Force per unit area gives the pressure. So I hope that up to here each and everything is clear to all of you. Now we will discuss this in quite detail. So for that, let's suppose we have a container. Take new slide. Okay, and now we take a container like this. So this is your container, and in this container you have fluid like this way. Okay, and in this fluid we can simply say that we have a point like this way. Take like this way. So here it is a point, let the point be A, B, C, P, whatever you can take. So the point is A, and you have to calculate the pressure on it. So what will you do? So firstly we will calculate the force. So pressure is nothing but force per unit area. So the basic thing is that force must be perpendicular force to the area. It means whatever liquid is upside of that point or the upper side of that point, that has a certain weight, we can simply say that, and the weight let be capital W. So that weight will be acted can be acted on that point. Okay, so basically here the force is equal to the weight, and the weight which is above that point or above that layer. Okay, so because I have already explained you that we consider the fluid as a ideal fluid, that's why we take the complete layer of this liquid or simply take a point. The situation are quite similar. Okay, so force and the force must be perpendicular on that point. So force, perpendicular force, and that must be applicable on that point, and we get a ratio. So perpendicular force per unit area, that gives us the pressure. So I hope that up to here each and everything is clear to all of you. Now for a homogeneous and non-viscous fluid, basically ideal fluid. Okay, so for an ideal fluid, this quantity does not depend on the orientation of delta S. Orientation means if we change the direction of the area. What it means? It means we can simply say that if we have a container, okay, and you take the point A like this way, so if we take area A like this way, okay, or we take the area like this way, okay, or we take the area like this way, so it means in any direction you can take your area, but the force must be perpendicular to that area. Okay, so this is the quite easy to understand that for an ideal fluid, because I have already told you that in place of the complete layer we take only a single point, because the fluid is ideal. It means for a point the orientation of the area doesn't matter, but if we take a layer, complete layer, then the area of the orientation of the surface matters. That's why we take the fluid as an ideal fluid. and in place of complete layer we take only a single point. Okay, so that we can skip the orientation of the surface area or the surface what we have chosen here. Okay, now what we will discuss about the ideal fluid we have, and we have discussed about the force, we have discussed about from where the force comes and what should be the direction of the force that must be taken for the calculation of the pressure. And after that we finally say that for a fluid, and the fluid must be ideal. Okay, the pressure is a scalar quantity having only magnitude, so it means we take the pressure as a scalar quantity. Now we will come to the unit of the pressure. So what should be the unit? Because we have the formula, that is the pressure equal force upon area. So force, the unit will be Newton, and divided by area, the unit will be meter square. Okay, so it can be rewritten as Newton meter inverse 2. So I hope and I believe that it is quite easy to understand, it is quite easy to learn what is the unit, is the unit of the pressure. Okay, and it also abbreviated as Pascal, because on the honor of Pascal. In the honor of Pascal, Pascal was a great scientist, so that's why we abbreviate the unit of pressure, that is Pascal, and in short it is written as PA, so capital P and small a. So that is basically the PA or Pascal or Newton meter inverse 2. So this is all about the pressure. This is all about what type of this quantity, this is scalar quantity, this is all about the unit of the pressure, what is the unit of the pressure. Okay, so I hope that each and everything is clear now. Now we will come to the next topic, that is the variation of pressure with height. The basic sense is from where we came an idea that there must be change in pressure, change, or we can say the variation. So variation of pressure with the height, so that idea from where it can come. We have gone through a practical, let be, if we take like this way. Let's suppose this is your container having fluid, okay, and let be this is your fluid inside it, this be, okay. This is the activity you can easily understand what I am trying to explain you. Now take any object and dip it in like this way. Okay, so if the direction of that body, the vertical direction of the body is like this way, as I have shown here, or we can say that the vertical must be at 90 degree with the surface of the fluid, and just you push that body inside it. Then what will you see? You will see that as you remove your hand, let's suppose the body is up to certain depth like this way. Okay, so this is the depth, let be x for example. So when you push that body at an angle of 90 degree with the surface of the fluid, then it goes down, let's suppose up to a displacement x. But the miracle occurs when you remove your hand, then you will find that the body just jumps like this way. Okay, so it jumps in the upward direction. What does it mean? It simply express it simply represent that we apply a force, let be F1, in the downward direction, but at the same time another force is F2, which is we can consider that applied by the layer which is at the depth x. So this is that layer which is below the distance x, and that layer applies a upward force F2, and you can imagine that the body jumps up. It indicates that the force F2 that must be greater than the force F1. And from where this force comes, because I have told you that the pressure is nothing but force per unit area, it means this force is generated by the pressure of that particular liquid and at that particular layer inside the liquid. Okay, so this is the layer which is considered as the depth x and applies a force F2. Okay, and if we take this one layer, okay, so this one layer can be taken as on the upper surface we can consider and has force F1. So we can conclude that due to the different layers has different ability to apply the force in the upward direction, this simply indicates that there must be a variation in the pressure. Now question, how we can calculate the variation in the pressure. So for that we have to consider here, like you can see in the picture in the diagram, that we have supposed different points in the vertical column of the liquid. So this is your container like this way. Okay, this is your the one layer, let be layer your B, and this one is your another layer of that liquid, that is layer A. Okay, so these are the two layers A and B, and as I have told you that in case of ideal fluid the layer can be simply represented by a point also. So this be a point B at layer B and this be point A at layer A. Okay, and that point enclosed by a surface. So we consider that that surface or a small surface delta S, and this is also covered by the same surface, so delta S. So both surfaces will be delta S1 or it can be taken as delta S2. Okay, so this be your liquid column containing, or we can say that having surfaces delta S1 and delta S2, having points A and B. So this is the liquid column, we can simply say that, which is considered as an equilibrium. Now what are the forces here? As you can see that let be a force due to the pressure of layer A, or we can say the pressure at point A, that is considered as F1. Okay, and here the force is considered as F2 due to the pressure at point B. So this is a liquid column, so it must have a weight also, and we know that the weight of each and every object is always downwards. Okay, so here in this case we have three major forces, F1, F2 and capital W. So F1 force is due to the pressure. We can simply say that let be the pressure of layer A, or we can say at point A, that is P. Okay, and this is the height that is taken as dz in the diagram, and up to height dz, let's suppose the pressure, if as I have explained to you that the force F2 is smaller than F1. Okay, it means simply say that the pressure at point A must be greater than the pressure at point B. Okay, so if we take the pressure at point B as P, then here it must be P plus dP. This is the variation dP. It means the pressure increases from layer B to layer A and from P to dP, and as a result at point B the pressure is P, at point A the pressure is P plus dP, and at layer B or at point B pressure is F2, and at point A the force is F2, and at point A the force is F1. So what we have written here, that is for point A and for point B. So for point A the pressure is taken as P plus dP, at point B the pressure is taken as P, at layer A the force is F1, at layer B the force is F2. Okay, so at point B pressure is small, so F2 will be small, and at layer A, at point A the pressure is larger, then F1 must be greater. Okay, now we consider that this liquid is inside a container. It means there is no motion, and if there is no motion, so we can consider that the liquid column must be in equilibrium condition, and if it is in equilibrium condition, then we can simply write that all the forces must be equal. So we have force like this way. This is your force F2. You can see in the diagram that one is F2, that is in the downward direction. So this is in downward direction. We have a weight that is also in downward direction. You can see in the picture this one. Okay, so F2 is in downward direction, weight is in downward direction, whereas the F1 is in upward direction. So F1 will be in upward direction, and this is your complete liquid column, as you can see. So in this liquid column we have three forces. Two is in downward direction, one is in upward direction, and the column is in equilibrium. How is it possible? It is possible only when we consider that F1 that is equal to F2 plus capital W. Okay, so as we have here that in the basic diagram you can see here the delta S1 and S2 that is considered as delta S. Okay, and we have already explained that at A the pressure is P plus dP, and at point B the pressure is P. Okay, so we can calculate simply that F1 will be equal to P plus dP times delta S, and F2 can be calculated as P times delta S. Okay, so we have the values of F1 and F2 in terms of pressure, so that we will use here. So F1 will be P plus dP times we can say delta S, and F2 we have P times delta S and plus W. So let be this equation 1. Now we will take that, as we know that we have weight, and weight is nothing but that is equal to mg. Okay, mass of the liquid column and multiplied by the acceleration due to gravity. and the mass is also written as density into volume into G. Okay, so in place of W we can write that it is rho times V times G, and the volume is nothing but that is area. So you can see in this picture that the area is taken as delta S, area of the liquid column, and the height is taken as dz. So in this time, this is the, we can say, the area, and the area is taken as delta S and the height is taken as dz. So in this liquid column, the volume can be written as the height into the height dz multiplied by area. So area into height, that becomes volume times G. So this is the value of the fate of the liquid column. Okay, now put the value of capital W in equation number 1, and what we get? We will get that P plus dP times delta S, and that must be P times delta S plus, and W, that is rho times delta S dz times G. Okay, so we have to solve it now and see what will we get. So firstly we will write here P plus dP delta S. So P plus dP times delta S, and that must be P into delta S. So P into delta S plus, and rho times delta S delta Z, rho times delta S, and that is dzg. So dz and G. So delta S can be taken as common and cancel out. So we have only P plus dP, and here we can write P plus rho times dz times G. Okay. Now P to P cancel out. We can simply, so P to P can be cancel out. So dP can be written as, that is equal to rho times dz times G. What it mean? As I have told you that the dP is the pressure which is increased at the layer A. Okay, so as I have told you that this is your liquid column, this is the layer A and this is the layer B. Okay, and this layer the pressure is P, and at layer A the pressure is P plus dP. Okay, so it means the dP means increase in the pressure, that is rho times dz times H. Now if we calculate the pressure at point A, then what should we do? We have to integrate it. So let's get started. We have a result that dP equal to rho times dz, rho times dz times G. So integrate of dP, so integration of rho times dz times G. Now what is dz? As I have told you that dz is the basically the separation between the two layers here, that is layer A, that is layer B, and this is the separation. As you can see here, this is dz, this is the separation. So if we talk about point B or the layer B, then dz must be 0. So if we take dz 0, and that is for layer B. Okay, and if dz is 0, then we can say that pressure is P. So pressure is your P. Now if your dz is taken as H, okay, so you can see here dz, if this is your H, so this will be for, we can say that for layer A, and the pressure is taken as P plus dP. Now we take this p that suppose p not this p that suppose p 1 maybe. Okay, so we can simply write that that dp, and this is rho times g times dz. When dz is 0, then pressure is p naught, and when dz is h, then pressure is p1. Okay, so this can be rewritten as that p1 minus p naught, and that is equal to h rho g. Okay, so it will be h rho g, or p1 that is equal to p naught plus h rho g. So this is the final result. As you can see that dz, that is the h, and that is for layer A, and the pressure is considered as P1 or P plus Dp. Okay, so this pressure will be at level A or the bottom layer. So we can simply say finally we have a conclusion that as we go deeper inside the liquid column, then the pressure increases, and that is directly proportional to the depth of that liquid column. So I hope and I believe that up to here each and everything is clear to all of you. Now what you have to do, you have to go through each and everything whatever I have told you. Try to understand each and everything by yourself. Just assume that you are sitting in front of a liquid column. We have different layers, different points. Liquid is in a stable condition, equilibrium position, and if there is equilibrium, then what type of forces must be there? Why we take a point in place of the layers? Okay, so what is the ideology behind this derivation? Okay, so these things you will go through once in your practical life, then I think and I suppose that it will be quite easy to understand. Okay, now what, just try to do this derivation by yourself, and if you feel any difficulty, then you can play and pause the screen and note it down. Okay, and if you have any doubt, then please comment, please message. Okay, thanks for watching me, thanks for listening, and the best of luck to all of you.